Welcome again to the videos for Shaughnessy's class. This is Probability and Set Theory Lesson 8. This is in fact the last taught lesson for this unit. Keeping in mind the disclaimer, please make sure that you're showing up to class because these are only kind of rough ideas. Going through this idea now. Probability and Set Theory 8, is all about multiple events. Dependent or independent events is what we call them, okay? And you'll see that. In fact, that's probably in the descriptor. If you've got multiple things happening, more than one event occurs, okay, the probability of a later event could be affected after the first one happens, and that's the key thing. Sometimes probabilities, after something happens, things change, okay? Sometimes they don't, okay? If I look at this one here, e.g., okay, hopefully you can read this, okay? A bag contains, I'll focus again. A bag contains 7 red marbles, 5 blue, and 2 yellow. From this bag, 2 marbles will be drawn, one after another, without replacing the first marble drawn. Okay? If we consider drawing a blue marble and then drawing a yellow marble, we need to recognize that the probability of the second event changes once the first event occurs. It was 2/14ths, but now it becomes 2/13ths because there's only 13 marbles left in the bag. There's still 2 yellows, okay? But the number of marbles left over has changed. So if I don't realize that, to begin with, it was 2/14ths to choose that yellow marble. But after I picked a marble, because I didn't put it back, okay, it's now 2/13ths. The probability has changed, and this is what we're talking about. This second example here, a bag containing 7 red, 5 blue, same context, 2 yellow. From this bag, 2 marbles will be drawn, one after another, replacing the first marble being drawn. Okay, if we consider drawing a blue, then drawing a yellow, same context, the probability of drawing the second marble is independent of the first event. That means it hasn't changed. It was 2/14ths before. Then that first event happened, and I plugged that marble back in. It's still 2/14ths after all is said and done. It doesn't matter what happened afterwards. It doesn't matter what happened first. So these are independent events. Whereas if I didn't put it back, it was dependent events. Now that's what we're talking about here, dependent versus independent. Is the probability of the second event or later events occurring dependent or independent of what happened first? If it's dependent, things have changed. If it is independent, things have not. That's these definitions here. Dependent events are events where the probability of the second event occurring changes because the first event has occurred. It depends on what happened the first time. Whereas independent, the probability of the second event occurring does not change. Okay? Well, even though the first one's occurred, even though it doesn't matter what happened first, it doesn't matter if anything happened first, the fact is that they're independent. So if I look at this one here, an experiment involves randomly selecting a coin from one bag and a marble from another box. Okay? A bag contains 3 dimes and 4 quarters. The box contains 7 marbles, each of a different color. Event A is selecting the dime. Event B is selecting a yellow marble. Okay? Are these dependent or independent? Okay. Now, I'm assuming that I'm selecting the coin first, so they are in order. Once I've picked my coin, okay, does the probability of selecting the yellow marble change depending on which coin I draw? No. There are 2 separate bags. They're 2 separate situations. The probabilities haven't occurred, or the probabilities haven't changed. So these are independent events. And it's because they occur in separate bags. The probability, I'm just going to write prob. The probability of selecting a yellow marble is unaffected. Okay. It's like flipping a coin and rolling a dice. It doesn't matter what happened first. The rolling the dice is still unaffected. It's still unchanged. Okay. If I look at this one here, e.g., an experiment involves randomly selecting 2 different students from a group of 7. Okay, Peter and Henry are in that group of 7. Event A is selecting Henry, event B is not selecting Peter. Are these dependent or independent? Well, it doesn't say that the students are replaced or whatever once they're selected, but it is saying that they are different. So if they are different, once I select one, then I can't have him in my list. So if they're different and I can't have him in my list, the second probabilities are going to change. Are these dependent or independent? These are dependent. And it's because the selection of Henry will affect the probability of not selecting Peter later on. Okay? When I did Henry, or when I was talking about Henry, and I'm randomly selecting Henry, there's a 1 in 7 chance of selecting Henry. Good. There's also a 6 in 7 chance of not selecting Peter. Once Henry's chosen, provided Henry's chosen or whatever, then what happens is the probability of not selecting Peter changes. If I've got Henry, there's a 5 in 6 chance left over. Okay? And if I didn't get Henry to begin with, I've still got a 5 in 6 chance. There are only 6 people left, and one of them is going to be Peter. So I've got this sort of idea. That second probability changes. And because of that, it's dependent on what happened first. Because of that, they're dependent events. It has nothing to do with the mathematics yet. Okay, I'm not looking at the mathematics of it. It has to do with the context. Now, continuing along with this, calculating probabilities, doing the mathematics behind it. Okay. If they're dependent events, the probability of A and B, okay, this occurring and then this occurring, the probability of A and B, if they're dependent on each other, okay, is the probability of A and times the probability of B occurring given that A has already occurred. Okay. That slash, it does go a little bit past the line in each case. It means the probability of B occurring given that A has already occurred. So that's dependent. That means that the second probability changes depending on what happened first. Written with the symbols, the probability of A intersection B is going to be the probability of A times the probability of B given that A has already occurred. Okay, same thing, same deal. Okay. And is a multiply. Okay, you're doing this and this. You're doing the first thing and the second thing. If it's independent, the probability of A and B, it doesn't matter what happens first because the second probability is unchanged. So you just do the probability of A happening times the probability of B happening because B's probability hasn't changed depending on what happened first. And with the symbols, it's the same thing. The probability of A intersection B is going to be the probability of A times the probability of B because it's independent. So you don't have to worry about it. The classification of dependent and independent comes from the context. But once you've chosen it, then you just do the multiplications. Okay? If I look at a question like this, an experiment involves randomly selecting 2 tokens from a bag containing 7 red, 5 blue, and 2 yellow. What is the probability of drawing a red token and then a blue token in that order with replacement between selections? So with replacement means I'm putting the token back. So whatever I get first, I'm putting back in. If I'm putting them back in, then these are independent. It's not changing. So I need to know the probability of getting a red and then a blue. Since it's not dependent, it's the probability of drawing a red token times the probability of drawing a blue token. The red token, going back here, there's 7 in total out of 14. So the probability of drawing a red token is 7/14 times blue token. So the blue token is going to be, there are 5 blues, and if I put it back in, I replaced it, there's 14 tokens still left over. So 7/14 times 5/14 is 35 over 196, because I'm multiplying top to top, bottom to bottom, reducing that if I can. Okay. That becomes 5 out of 28. And that's my solution. Okay. They're independent. But it came from the context. Now, not all of these are going to be the same, so we'll just keep going. B, finding a red token and then a blue token. Okay, in that order. Okay, it's almost the same, without replacement between selections. Well, in this case here, it's the probability of drawing a red token and a blue token, but these are dependent events. So it's going to be the probability of drawing a red token times the probability of drawing a blue token, given that I've already drawn a red token. Okay? The red token is still 7/14. Nothing's changed. The blue token is still 5. There's still 5 blue tokens, but if I've already drawn the red and I haven't put it back, there are only 13 tokens left. So that second probability became 5 out of 13. And so I have 7/14 times 5/13, and I want that as a fraction, and that reduces to 5 out of 26. Okay, I just did the math and simplified it. Be 35 out of 182, I think. So you get that. Okay, and so this sort of idea, you have to think about what's going on. Is there a dependency situation? Okay. Now I'm keeping in mind the order thing, and I'm going to come back to that in a bit. Here, drawing 2 yellow tokens without replacement. So it's going to be the probability of drawing a yellow and another yellow. Okay, I'm not replacing them, so it's going to be the probability of drawing a yellow times the probability of drawing another yellow, given that I've already drawn a yellow. Okay, so these are dependent because it's without replacement. The probability of drawing a yellow is 2 out of 14. The probability of drawing that last yellow, well, I've drawn one yellow, so there's only one left, but there's only 13 tokens left in the bag. So I get 2 out of 14 times 13, and I think I just said this, but I'm going to actually figure it out. It's 182, which is 1 out of 91 reduced. Okay, so that's that. You just have to ask yourself whether it's dependent or independent. B and C are dependent. I'm going to write dep here. And dep, because it depends on what happens first. Okay, you got to think about that classification. D, drawing a red token and a blue token with replacement. Now the key thing here is I didn't say in that order. So I could have a red token first and then a blue token, or I could have a blue token first and then a red token. So I've got the probability of drawing a red and a blue, plus the probability of drawing a blue and a red. So I've got to keep those in mind. Now, with replacement. So since there's replacement, it means they're going to be independent. So I'm going to end up with the probability of drawing a red token times the probability of drawing a blue token, or plus the probability of drawing a blue token times the probability of drawing a red token. I don't need to consider the whole given that it's already occurred, because these are with replacement, these are independent. So from here, red token is 7 out of 14. Times blue token, there are 5 out of 14. Okay, I actually did this before. 7 out of 14 times 5 out of 14 is way up here, and A is 5/28. Plus, I'm going to get 5 out of 14 times 7 out of 14. It's also going to be 5 out of 28, which is going to end up giving me 10 out of 28, which is 5/14. There's a 5 in 14 probability that this occurs. Okay. I just did the math, but since I'd done this multiplication before, I knew it was 5/28, so I cheated. 5/28 plus another 5/28. 5/28 plus 5/28 is 10/28, which I then reduced. So I cheated. Okay, you may end up doing more work, and that's fine. Okay. E, drawing a red token and a blue token without replacement. Okay, drawing a red token and a blue token without replacement. So the only thing that's going on here is I've got, it either could be a red and a blue, red and a blue, okay, or the probability of drawing a blue and a red. But the thing is, I've got to consider the fact that one happened first. So the probability of drawing a red times the probability of drawing a blue, given that a red has already occurred, plus the probability of drawing a blue times the probability of drawing a red, considering that a blue has already occurred. Okay, so I end up working this out. Okay. Probability of a red is 7 out of 14. A blue, given that a red has already occurred, is 13. I've actually done this one up in B. Plus, okay, probability of a blue is 5 out of 14. Times a red is 7 out of, but there's only 13 left. I end up getting the same thing all the way through. 7 times 5 over 14 times 13 is 5 out of 26. 5 out of 26 plus 5 out of 26 is 10 out of 26, which reduces to 5/13. Okay, so once again I cheated because I'd done this in B and I'd done something almost identical to this in B. So since I know they're the same, I just put them together. Okay, so you've got that. Now the only thing that happens is, what are the odds? Now I've suddenly said odds. Oh goodness, you got to watch for that. What are the odds in favor of drawing two blue tokens without replacement? So I'm not replacing them. So the first thing I need is the probability of getting a blue token. So I need the probability of a blue token and another blue token, which is the probability of a blue token times the probability of drawing a second blue token, given that I already drew one. So a blue token is 5 out of 14 times. If I've already drawn one and I'm not replacing it, there are only 4 blue tokens left out of 13. So I end up with that, which is 20 over 182, which then reduces. And I'm just going to reduce it really quickly. I could do it in my head. Actually, it doesn't reduce much. 10 over 91. Okay? That there is the probability of drawing 2 blue tokens. 2 blue tokens, 10 out of every 91. It wants the odds in favor. So there are 10 favorable and out of the 91 to possible, or 81 that aren't. 10 to 81. Okay, I just did 91 minus 10. I got that. Okay, so it's 10 to 81 odds. So you can start asking odds, and either way the same thing happens all the way through. You've just got to make sure that this is going on. It's all this idea of dependent versus independent. If I look here, if A and B are independent events, P at A is 0.3, P at B is 0.65. Find P A intersection B, which is P A intersection B. It's a AND situation. Okay, so this is going to be P at A times, now they're independent, so it's just going to be times P at B. So P at A times P at B is 0.3 times 0.65, okay, which is going to be, and you just go to your calculator, 0.3 times 0.65, it's going to be 0.195, I could do that, okay, 0.195, and I would probably leave it at that. Okay, I could turn that into a fraction. It's 195 over 1,000. I could do that. Okay. Here, if it wants PB intersection A, so the probability of B intersection A. Okay. It's going to be the probability of B times the probability of A, which is going to be 0.65 because they're independent, times 0.3, which is going to be the same thing. Okay. Okay. Now, once you're going on with that, you just have to watch, because we're going to try to fit that, mix this up. P of A intersection B prime. So the A intersection B prime is the probability of A and B prime, which is going to be the probability of A times the probability of B primed. B primed being the complement. Probability of A is 0.3. Probability of B primed is 1 minus this. So it's 0.35. Okay, because it's the complement. You get 0.3 times 0.35, and you get 0.105. That is the probability of A intersection B prime. If I do this, probability of A primed intersection B primed, it's the same idea. A primed intersection B primed. It's going to be the probability of A primed times the probability of B primed. Okay? Probability of A primed. Well, A was 0.3, so A primed is going to be 0.7, and B primed is 0.35. So I work this out, 0.7 times 0.35, and it works out to be 0.245. Okay, so you just have to watch what's going on. You have to understand the symbols. I'm using intersection for AND, okay? Keeping in mind how you think of intersection as being part of the A for AND. So I go from there. Now if I go to this next example, e.g. if A and B are independent events, so they're not dependent on each other. P of A is this, P of B is this, find P, A, intersection B. All primed. Okay? So P, A, intersection B, all primed. P, A, intersection B, all primed. So not both of them occurring at the same time. So one may be, but not both. Okay? This is going to be 1 minus the probability of A intersection B. Okay? Because it's the complement of A intersection B. So the complement of A intersection B is 1 minus P of A intersection B. Okay? It's all one thing. It's a little bit different than the primes on the individual pieces. So it's going to be 1 minus the probability of A times the probability of B, which is going to be 1 minus probability of A is 0.3, probability of B is 0.65. So it's going to be, I'm just going up here, 1 minus 0.3 times 0.65 is 0.195. So 1 minus that is 0.805. This is the complement of the compound event. Now this is a little bit hard, and you won't have to do this much, but nonetheless it's there. It's the complement of the entire operation, the entire union or intersection idea. Okay? So continuing on with this, then I've got example. If A and B are dependent events, P at A is 0.3, P at B is 0.5, and P of A A given B has already happened. That's the best I can do when I'm typing this slash. Okay? P of A given that B has already occurred is 0.4, and the P of B given that A has already occurred is 0.35. Find the following. P of A intersection B. So the probability of A intersection B. Okay? They are dependent. So I need to look at here. That's going to be the probability of A times, since they're dependent, it's the probability of B given that A has already occurred. So now I need to look here. Which numbers do I need? Probability of A is 0.3. Probability of B given that A has already occurred is 0.35. That's this one here. So I make that, and I do that math. And multiplying those out, I get 0.105. Okay. If I look at this one, the probability of B intersection A. They're dependent, so that's the probability of B times the probability of A given that B has already occurred. The probability of B is here, it's 0.5. Probability of A given that B has already occurred is right here, 0.4. Multiply that out, I'm going to get 0.2. And so once I'm comfortable with that, then all I do is just keep going. Sorry, I paused that one. Going on with this. So refocusing it. If A and B are dependent events, so they depend on each other, and A intersection B, so A intersection B is 0.28, P of A is 0.6, find the P of B given A. So I know that the probability of A intersection B is equal to the probability of A times the probability of B given that A has already happened, because they're dependent. Now this question here has already told me this one. I know this is 0.28. equals P at A is 0.6 or 60 times this one, P of B, given that A already exists. I don't know what that is, but I can just find it using algebra. Divide by the 0.6, divide by the 0.6, and I'm going to get that the P of B, given that A has already happened, is going to be 0.28 divided by 0.6, and that is going to be 0.4666 repeating, or rounded 0.47. Okay, so that's what I get. Okay, it's just working backwards. Now that's dependent and independent. Okay, once you're comfortable with that, you can look at some of these things. You've probably heard situations of don't drink and drive, because if you drink then drive, your probability of getting into an accident or killing somebody or that sort of thing is increased. Or make sure you study, because if you study, you're more likely to pass the exam. Now, there's mathematical basis for all of these things. What you're trying to do is you're trying to figure out whether they depend on each other, whether the probability of something changes because something else already occurred. So what you do is you test to see if they're independent. You test to see if they don't change. And if they don't change, then there's no relationship. If they do change, then there's some relationship, and we don't know what it is, but there's some relationship, and you can analyze it much further. So if this one here, I just use this guy. Based on past history, the probability that Bob studies for an exam is 0.35. The probability that Bob passes this exam is 0.8. Determine if these events are dependent or independent if the probability that Bob passes when he doesn't study is 0.65. So, if he passes when he doesn't study is 0.65. That's the probability, okay, of a pass, when not studying. So intersection not study. Okay, the probability of a pass when is not study, okay, is that. Or the probability of passing when you've got the complement of study. Okay, and we know that that is 0.65. Now, if these are dependent, then I won't be able to make this work, because this is requiring them to be independent. So I'm testing, are they independent? If they're independent, all the mathematics works out. So it's going to be, if they're independent, it's the probability of a pass times the probability of not studying. Study primed. And that should equal 0.65. Okay? If they're independent, which means there's no relationship between studying and passing, this will work. So I'm testing to see if it works. The probability of passing, okay? The probability of passing the exam is 0.8. So that's good, okay? The probability that he doesn't study, well, I look at this. It's a 35% chance that he studies, a 65% chance that he doesn't. So 0.65 there. If this is true, if these aren't related in any way, shape, or form, if there's no relationship between studying and passing, then this is correct, because that's what I'm guessing. Is this correct? Do these equal each other? And I go figure this out. Those of you that are astute can see that it isn't, okay? I get 0.52 on one side, 0.65 on the other. So is this independent? No. It's not independent. There has to be some relationship between these things. Okay? And so since there's some relationship between these things, then they are dependent. Okay? So therefore, since they are not independent, then they must be dependent in some way. Okay? I don't know the specifics, and you don't need to know the specifics right now. Okay? You're just testing the idea. Are they dependent or are they independent? And if they are independent, then you're happy. This equation works. If they're not independent, then you need some sort of other information. You need to know what's the probability of studying given that you've, or what's the probability, of passing given that you've already studied, because there's some change going on there. And I don't know what it is, but there's some change going on there. So once you're comfortable with that, you've got this idea. That's the idea between dependent and independent events. There are multiple events. Does the probability of the second event occurring change depending on what happened first? If you have any questions, please come see me in class, and otherwise, have a great day.